Chapter 8, Anatomy of Anterior Chamber and Drainage Angle. Page number 282. The outflow apparatus. The features of the outflow apparatus are as follows. 1. Internal scleral sulcus. A. Sulcus. B. Shaw-based ring. C. Scleral spur. 2. Trabecular meshwork. A. Uveal meshwork. B. Corneoscleral meshwork. C. Trabecular structure. D. Iris processes. E. Pericanalicular connective tissue. F. Extracellular matrix. 3. Canal of Schlemm and collector channels. A. Schlemm's canal. B. Endothelial lining. C. Giant vacuoles. D. Collector channels. 4. Intrascleral arteries of the limbus. 5. Innervation of the outflow apparatus. 6. Uveoscleral drainage pathway. 7. Location of the resistance to outflow. 8. Regulation of ocular pressure. 9. Aging and the outflow apparatus in primary open-angle glaucoma. Internal scleral sulcus. The sulcus. The sulcus is a circular groove on the inner aspect of the corneoscleral limbus, extending from the termination of Descemet's membrane anteriorly demarcated by Shaw-based ring to the scleral spur posteriorly. The portion of the spur which forms the posterior boundary of the sulcus is sometimes called the scleral roll. The sulcus completely accommodates the canal of Schlemm externally and the corneoscleral portion of the trabecular meshwork internally. Shaw-based ring. Shaw-based ring is the anterior border ring of the trabecular region and contains circularly arranged collagen fibers, periodicity 64 nanometer, intermixed with elastic fibers. With age, there are also patches of long spacing or curly collagen. The ring marks the transition between the corneal endothelium and the trabecular cells and also the termination of Descemet's membrane, which however may split at times to enclose the inner and outer aspects of Shaw-based ring and may show fine extensions into cortical zone of the uveal trabeculae. Scleral spur. The scleral spur is a wedge-shaped circular ridge which marks the deep aspect of the sclerolimbal junction. It receives the insertion of the anterior tendons of the longitudinal ciliary muscle on its inner aspect. Its anteromedial base forms the posterior margin of the scleral sulcus and receives the posterior attachment of the corneoscleral meshwork. The scleral spur contains collagen and elastic tissue with a circular arrangement like that of the trabecular beams of the corneoscleral and cribriform or juxtacanacular meshwork with which it blends. The collagen fibrils vary in diameter from 35 to 80 nanometer and widen towards the sclera. The connective tissue components are continuous with those of corneoscleral trabeculae, where they become covered by trabecular cells. Contraction of the ciliary muscle pulls the spur posteriorly and opens up the trabecular spaces. This is a likely mode of action for myotics to reduce outflow resistance. Recently, it has been shown that there are contractile myofibroblast-like cells oriented circumferentially within the scleral spur, which have sparse mitochondria and are rich in smooth muscle, alpha-actinin and myosin. They have an interrupted basal lamina and lack the desmin and intermediate filaments characteristic of the adjacent ciliary smooth muscle cells. These scleral spur cells form tendon-like contacts with the elastic fibers of the scleral spur, which are continuous with those of adjacent trabecular meshwork. Thus, changes in scleral spur cells, their tone might modulate outflow resistance by altering trabecular architecture. Some trabecular meshwork cells also stain positively for smooth muscle, alpha-actinin and smooth muscle actin. Individual SSC, that is, scleral spur cells, are innervated by unmyelinated axons, which derive exclusively from neurons that run forwards in the supraciliary space. They contrast with the myelinated axons, which supply the mechanoreceptors of the scleral spur. The axons run circumferentially in the scleral spur parallel to the arrangement of the connective tissue elements, and their terminals contact the cell membranes closely without an intervening basal lamina. The nerve endings contain granular and agranular vesicles, generally regarded to be characteristic of adrenergic nerves. But this is not confirmed by immunohistochemistry. An adrenergic innervation of the monkey scleral spur has been reported and is in keeping with our knowledge of anterior chamber innervation in these species. However, note that similar vesicles have been observed in non-adrenergic terminals in the anterior nervous system. The ciliary muscle cells receive a dense cholinergic innervation, whereas the varicose axons, which innervate the human SSC, that is scleral spur cells, are immunoreactive for NPY, SP, CGRP, VIP, and NO, and are negative for acetylcholinesterase. The posterior trabecular meshwork receives a similar innervation, a parasympathetic origin for the VIP and nitrogen fibers of the scleral spur from the pterygopalatine ganglion is quite likely, given that such fibers contribute to ocular innervation in the human and primate eye. There is also possibility that some of these fibers may arise in the human eye from the intrinsic VIP and nitrogen fibers of the choroid, in which region these transmitters are also co-expressed. It is of interest that in the monkey, where the intrinsic plexus of the choroid is much smaller than in the human, no VIP or nitrogen fibers are present in the scleral spur. Although most NPY positive neurons are localized in sympathetic fibers, some neurons co-express NPY and VIP and are thought to have their origin in the parasympathetic pathway via the pterygopalatine ganglion. Most, but not all, SP positive fibers innervating the SSE, that is, scleral spur cells, were also positive for CGRP. But all CGRP positive fibers co-localized with SP. The precise origin of these fibers is not known. Most of the fibers exhibiting co-localization are likely to be sensory fibers that derive from the trigeminal ganglion. Of those fibers which are positive for SP but negative for CGRP, it may be noted that a similar co-expression has been demonstrated in the pterygopalatine and ciliary ganglia in cynomolgus monkeys. The complex peptidogic and nitrogic innervation of the SSE, that is scleral spur cell, is thought to provide a basis for modulating the resistance of the outflow pathway through the tendon-like contacts of the SSE, that is scleral spur cell, with the elastic fibers of the trabecular meshwork. In the cynomolgus monkey, injection of VIP or of various nitrovasodilators causes an increase in outflow facility. Figure 8.5, meridional section of the scleral spur in a human eye. A. The scleral roll forms the posterior boundary of Schlemm's canal SC, while the sloping anteromedial border of the spur provides attachment for the corneoscleral trabecular sheaths TM. The meridional muscle fibers of the ciliary body CB are inserted into the posterior edge of the spur. The uveal trabecular sheaths pass below the spur. C is equivalent to peripheral cornea. SS is scleral spur. Figure 8.5b. The elastic element of the spur, seen as dense dots and lines, arrowheads, depending on the plane of section, is distributed predominantly around irregularly shaped bundles of collagen fibers. These extracellular elements are continuous with those of the corneoscleral trabeculae CT. The ciliary muscle fibers MF terminate into the spur. SC stands for Schlemm's canal. Original magnification 880 times. Figure 8.6a. Anterior terminal of trabecular meshwork into deep corneal lamellae and anterior ring of Schwalbe arrow as seen in the light micrograph of meridional section of the human eye. Original magnification is 220 times. Figure 8.6b. Higher magnification of the ring of Schwalbe SR. Dot-like structures represent transversely cut elastic fibers Descemet's membrane (DM) shows nodular profiles of Hazel-Henle warts. Note the termination of trabecular sheaths into deep corneal lamellae and transition of corneal endothelium. The transitional endothelium arrow contains trapped pigment granules. Original magnification 895 times. Thank you.